Hi guys, my name is Cheyenne McDorman, and today we're going to go over Module 4 and 5, which cover symmetry, transformation, and angles. So first we're going to figure out what a ridge motion is. So what is a ridge motion? A ridge motion is any way of moving all the points in the plane. There are 4 types of ridge motion. The first type is translation, a function that moves an object a certain direction. So in this picture, it shows a trapezoid being shifted or moved to the right. Next, we have rotation. It is a transformation that turns a figure about a fixed point called the center. In this picture, the trapezoid is rotated on this point to create this figure. Next, we're going to talk about reflection. A reflection is a mirror image of a figure flipped over a line or an axis. So in this picture, the trapezoid is flipped over this line to create the mirror image of the original figure. Then there is a non-ridge motion, which is a dilation. It is a scale up or down of a figure, simply changing the size of the shape. So this right triangle has been scaled up to get to this figure. Alright, so now that we know what a ridge motion is, we're going to resume to question 1. Question 1 says Devontae and Ephraim created a rotation ridge motion when they were supposed to reflect. Keep in mind that a reflection is supposed to be a mirror image of the figure. So this is what they created. This is the original figure that they were looking at. They had to create a reflection, but they did a rotation. This is their figure. So what they did was rotated the original figure all the way around, which is not correct in this situation. What they needed to do is draw a line next to the original figure and flip that figure to create the mirror image. This would be counted correct. So moving on, what is symmetry? Well, what is symmetry? Symmetry is the quantity of being made up exactly similar parts facing each other or around an axis. So there are 3 types of symmetries: one-line of symmetry, rotational symmetry, and reflection. Let's start with the first one. One line of symmetry is a figure that only has one possible line of symmetry where it looks the same on both sides of the line. Rotational symmetry is the number of distinct orientations in which it looks exactly the same for each rotation. Reflection symmetry is a figure that has several lines of symmetry where it looks the same on each side of the line. So let's look at some examples. So this triangle would only have one line of symmetry, because when you fold along this line, it'll look exactly the same on both sides. But it does not have a horizontal line of symmetry, because if you fold this point over the horizontal line, it will not look the same. So an example of rotational symmetry would be a circle. So anywhere you fold on these lines, it'll look exactly the same on the circle on each side of that line. Reflection symmetry would be a rectangle. So when you fold it, the piece of paper or a rectangle, vertically, when you hold out landscape, you create what is called reflection symmetry because it's the same on both sides. When you fold it horizontally, you will still get the same thing on both sides. So now that we know what symmetry is, we can now move on to question 2. So question 2 wants us to identify the types of symmetries for the figures. And the figures that are given are these right here. So let's put them in a chart. So this chart has 4 sections. One line of symmetry but no rotational symmetry but no reflection symmetry, one line of symmetry and rotational symmetry, or no symmetry at all. So the first one had 4 figures that match the description. So when you fold this triangle horizontally, you'll get the same. But if you fold it vertically, you will not get the same image on both sides. The half circle only has 1 line of symmetry. Yes, in the previous slide, a circle has rotational symmetry, but in this case, since it's a half of a circle, it only has 1. Now, on the previous slide, a rectangle had more than 1 line of symmetry, but in this case, it does not have rotational symmetry, so it only has 1. Same goes with the rhombus. It has 2 lines of symmetry, but it's asking for 1 line of symmetry, but no rotational symmetry. Well, a rhombus does not have rotational symmetry, so it is counted as the 1 line of symmetry, but no rotational symmetry. So there was no rotational symmetry but no reflective symmetry figures in this group of figures. But there were 2 figures that matched the description of 1 line of symmetry and rotational symmetry. That would be the equilateral triangle and the hexagon, because when you put lines of symmetry on there, so vertically, and then you turn it and you put another line of symmetry from point to base, and then you turn it and do the same thing, you'll still get the same figure on both sides of the line. Same goes with the hexagon. Anywhere you put that line of symmetry, you'll get the same figure on both sides of the line of symmetry. So there were 2 figures that we could not get symmetry at all. And because you could not fold them vertically or horizontally or diagonally to get the same figure on both sides. So now we're going to move on to question 3. Question 3 wants us to look at a vertex figure of a regular pentagon, hexagon, and an octagon. And Mariah has provided us a figure. But what is a vertex figure? A vertex figure is a figure exposed when the corner of a polyhedron or a polytope is sliced off. This is the figure that she provided for us. So how do we figure out if this is a vertex figure? Step 1. We need to add the interior angles of the pentagon, hexagon, and octagon, which is 108 plus 120 plus 135, which will give us 360 degrees. But wait, doesn't a polygon have an interior sum of 360 degrees? That is correct. A polygon has a sum of 360 degrees for the interior angles. Mariah's figure has a total of 363. So that means that there is a 3-degree gap between the original sum of a polygon. That means that Mariah's figure is slightly overlapped between the polygons. So we're going to move on to question 4. Question 4 wants us to talk about congruency. So they believe that triangle QPT is congruent to triangle SPT, which QPT would be this triangle right here. So how do we determine that? Well, we're going to look at the angles first. These angles are similar angles because they are acute angles. An acute angle is an angle that is less than 90 degrees. And also, how do we tell if they're similar angles? If we fold this figure in half, it'll match on both sides of the figure, where the points of where the angles are will line up with the other side of the triangle or the figure. So let's assume that these triangles are the same. So if angle T could be 40 degrees, then the angle T of triangle SPT would also be 40 degrees when you flip it on both sides. So they assume that angle QPT is congruent to angle SPT. Well, if triangle QPT is congruent to triangle SPT, and angle QPT falls on triangle QPT, then the angle SPT is congruent to angle QPT because the points of the angle, or point P, would be the same on both sides of this figure. So they assume also that triangle QPV is congruent to triangle SPV. So let's assume that angle B could be a 90-degree angle and angle Q would be 45 degrees. Well, we know that the interior sum of the angles for a triangle is 180 degrees. So if we assume that one angle was 90 degrees and the other is 45 degrees, we're going to subtract both of those from 180 degrees, which will give us 45 degrees, which will be angle P. And since when you fold the figure in half, angle P is lined up with the same as angle P of triangle SPV, it'll also be 45 degrees. Also, triangle QPV is the same type of triangle as SPV, which is a right triangle. Well, how do you know that it is a right triangle? Well, they say that that angle is a right angle, but why? That angle falls on line M, and a line equals 180 degrees. And well, 90 plus 90 equals 180 degrees, so both angles, QVP or SVP, will be right angles. Now let's move on to question 5. Question 5 wants us to inscribe some shapes into this circle. So the first shape that we're going to inscribe is this pentagon. So we're going to do that. There it is. So next we're going to inscribe this triangle into this circle. There it is. You will notice that angle P in both the triangle and the pentagon will line up at the same spot on the circle. That's angle P. So how do we figure this out? So we're going to look at the center point O, and then we're going to look at this angle. So the angle NOQ is equal to 24 degrees. Well, how do you know that? The central angle of a pentagon is 72 degrees. The central angle of an equilateral triangle is 120 degrees. So 120 minus 72 equals 48 degrees. Well, if you extend the line from NO to E, you will notice that NOQ separates that angle. So if this angle was 48 degrees and it's split in half by NOQ, that means that it's 24 degrees on both of these angles that make up NOE. So we're going to look at question 6. Question 6 wants us to look at this really cool picture of Jenny standing on a rock looking at a cliff. Well, she's holding a ruler out 2 feet in front of her. And the top of the bottom of the cliff line up with the mark separated by 1.5 inches. She is also a quarter of a mile from this cliff. So we need to keep in mind that 1 mile equals 5,280 feet. So we're going to convert these. So let's find out what a quarter of a mile is. 5,280 divided by 4 equals 1,320 feet. Now we're going to convert the 1.5 inches into feet. So 1.5 divided by 12, which is 12 inches in a foot, will give you 0.125 feet. So when you plug it into the equation, it'll be 1.25 feet over 2 feet equals the height of the cliff equals 1,320 feet. So when you multiply 1,320 feet to both sides, you are left with the height of the cliff on one side, which equals 1.25 feet times 1,320 feet over 2. So when you multiply the top two numbers together, you're going to get 165 feet over 2. So you're going to divide the top number by the bottom number and we'll get 82.5 feet. But in this case, they're wanting us to round by the whole nearest whole foot, which will give you 83 feet. So this cliff, from top to bottom, is 83 feet. So we're going to leave this video off with this ink blot. This ink blot is symmetrical when you put a line down the middle. It'll look the same on both sides. I hope this video was informational, and I hope you have a wonderful day. This is Cheyenne McDorman signing off. Bye.